Hello and welcome back to AB 474, Indoor Environmental Control. And this is going to begin our section on, that is chapter 5 in the book. Heat Transmission in Building Structures is the title of the chapter in the book. And I guess to paraphrase that, I would say it's heat transfer as it relates to buildings and structures and energy transfer. So we're going to begin by looking at some terminology, and then we'll review the three primary modes of heat transfer: conduction, convection, and radiation. We'll talk a little bit about latent heat transfer with evaporation and condensation, and then we'll look at mixed mode heat transfer, where we're combining the various modes of transfer. The purpose of this section, this chapter, is to start looking at energy transfer through our building structure, through our what we call the envelope of the building, and we will use that in order to help inform us as we move forward, trying to understand calculations for ventilation, for energy utilization in order to control the environment within a space or the environment within our envelope. So the videos for this will be broken into 5 different videos. So the first one will cover terminology and conduction. The second one will cover convection with an example. The third one will cover radiation with an example. The fourth one will cover evaporation and condensation. And then the final one will cover mixed mode heat transfer with some examples. So let's go ahead and get started. And we'll begin with some terminology. So I already used this term, but let's define it so that we understand what we mean when we say the building envelope. So we're talking about the structure that encloses our space, or the structure that makes our building enclosed. And it's going to include anything that's anything that is composing the outer structure of the building. So walls, roof, floors, doors, and then another word you need to learn is fenestration, which is referring to typically windows, but whenever we use the word fenestration, it's things with a material that can allow some light to pass. Typically it's made of glass, so windows. And in terms of thinking like an engineering analysis, so in terms of thinking for engineering analysis, this is the part of the building where energy enters and leaves. So we've already said that we bring some energy in with our ventilation air. So the air that we're moving around, the moist air has properties, so enthalpy, which is energy, and that can be carried in and out. The structure itself is the part of the building where energy crosses, another part of the building where energy crosses in and out of the building. And when we want to talk about energy moving, in this case we're looking at thermal energy most of the time, not always. We could be looking at mass as well. But if we're talking about thermal energy, then what we really like in terms of desirability is thermal resistance. And so this is the property of a material that determines how much energy can flow through that material. So the property of a material that determines how easily energy can pass through that material. And so a material that has higher thermal resistance is going to have less energy transfer. Right. And then most of you, I expect, have seen an introduction to heat transfer. So let's quickly review the primary modes of heat transfer, which are conduction, convection, and radiation. And then other modes that we're going to look at. Evaporation and condensation. And in reality, our modes of heat transfer are happening simultaneously, so we need to be able to handle them simultaneously. And so we call that mixed mode heat transfer. All right, so those are the primary vocabulary, new vocabulary or refresher vocabulary and definitions that we need to be aware of. So let's go ahead and start with our first mode of heat transfer that we're going to review, which is conduction. Okay, and when we say conduction, conduction occurs when we have heat transfer or thermal energy transfer between two objects that are touching. So that's a requirement to have conduction. And in terms of potential for heat to transfer, the heat or the energy is going to transfer from areas of higher temperature to lower temperature. And so conduction can happen within an object, or it can happen between two objects that are touching. So we don't have to distinguish that, a single object, we're looking only at the surface of that object, because conduction can happen within the object as well. And so you can have a temperature gradient within the object, where you have conduction moving within that object from an area of higher temperature to lower temperature. And the same thing, if you have two things touching, the energy is going to flow from the one that's higher to the one that's lower. So let's remind ourselves of the governing equation for conduction heat transfer. And so we're gonna look at part of the derivation of the conduction heat transfer equation. So in this governing equation, this little t represents our temperature profile. So it's that the temperature within all of the solid pieces that are touching. And so we're calling that a higher temperature the energy is going to flow from a higher temp to a lower temp. So you're going to have a profile within the material. You could potentially have a material that has an internal heat generation. A little k is our thermal conductivity of our material. Alpha is our thermal diffusivity. It's determined by the thermal conductivity and the density and C sub P. And then tau is time. So this is our overall governing equation for understanding conduction heat transfer. And we're going to take that equation and we're going to manipulate it a little bit with some simplifications that are appropriate for applications in heat transfer within buildings. So within our structural setting, we don't expect to have heat generation within our structure. At least we hope we don't have heat generation within our structure, which makes the Q-gen portion 0, which simplifies the equation one step. And if you recall from calculus, this looks a bit like a Fourier equation. We also, when we work with our systems for analysis, we typically assume that we are at steady state. And if we make that assumption, then we get an equation that looks a lot like a Poisson. And if we put the two of those together, steady state and no heat generated, then our equation drastically simplifies and looks a lot like a Laplace. And if we want to take this Laplace and expand it out for the 3 dimensions of our wall, we end up with looking at our temperature profile equation in terms of partial differential equations with respect to each of our axes. So the reason that we can make those simplifications is that in terms of what we're looking at in this class, most of our structures are what we call light structures. If you end up working in settings where you're with industrial settings, the steady state especially may or may not be a valid assumption, and so you may have to work with the dynamics of the building. But for what we're working with in this class, we are going to make the assumption that we are at steady state, because we are going to say we're working with light structures or light buildings. And so what does that mean, that we're working with a light building? In terms of this steady state assumption, let's put our temperature profile and time, T and T. And let's say that we have a a temperature, and at some point we change the set point. So we're initiating a change in temperature of our structure. There will be some lag in the temperature change. So there's our lag. But then we start to see an impact, or the actual temperature within our structure starting to change. So it's starting to change, and then it's going to go to the new set point. If this change happens within about 2 hours, then we call that a thermally light structure. But if that change takes much, much longer, then we call that a thermally massive structure. When we're working with thermally light structures, the change, so a change can happen fast enough that we can achieve steady state. In a thermally massive building, the lag is much, much longer, and so the situation becomes more dynamic because you have your external forces likely changing before you ever reach the steady state. Okay, so that's the difference between thermally light and thermally massive. So with a thermally massive, within 2 hours, the conditions surrounding, so change of set point is one thing we can do. Other things that can initiate this change in set point, or this change, it doesn't necessarily have to be a set point. Weather, so with sun going up, sun going down is a big change in the conditions that are impacting steady state. So if your structure can come to steady state within about 2 hours, we say, okay, then we can make a steady state assumption. And if it takes much longer than that, chances are the external influences have changed before your structure ever came to steady state. So we say that we have to deal with that situation as dynamic. So let's look at a quick example of convection. And we have a material, and on one surface we have temperature 1, and on the other surface we have temperature 2. This is our x-axis and our length L. So let's just say 0 and L, makes that better. So we'll start with our governing equation here, and you don't have to write out from the beginning every single time, but we're going to step through it. And then once we get to the main governing equation, you can just use that one. So the derived governing equation, you can use that one. All right, so this is an example, I guess, to kind of step through and take a look at the Laplace application and move a little bit toward our conduction equation that we're accustomed to seeing. So we have the Laplace equation, so we've assumed that we're at steady state and we have no heat generation, and so this is our governing equation. So let's let our temperature profile be C1x plus C2. And so basically this is just saying that we have some linear temperature differential. So that means that our first derivative with respect to x is C1, and our second derivative with respect to x is 0. So now let's find our C1 and our C2. We need two boundary conditions and we have two boundary conditions and we have two unknown constants. So we have our boundary conditions and we have our unknown constants, C1 and C2. All right. So let's find C1 and C2. So if x equals 0, then t equals to t1, which is equal to c2. And for the case where x equals to L, t equals to t2, which is equal to c1 L plus c2. 2. And if we solve that for C1, then we get C1 equals T2 minus T1 over L. All right, and then if we put those back into our equation above, then we get our temperature profile is equal to T2 minus T1 over L times X plus T1. All right, and let's just check it. So T0 is equal to T1, and that's what we expect. And T at L is equal to T2 minus T1 plus T1, which is equal to T2, and also what we expect. Okay. So just a little exercise to kind of demonstrate the governing equation in practice. So let's keep moving on with that in order to step into what we see commonly as the governing equation. And so this is equation 5.1 in your HVAC text. And it is so if we go back up and grab the Fourier equation, this is the steady state version of the Fourier equation. So it's written a little bit differently, but it is the same equation. So we're gonna say Q, which is our heat transfer, is minus K, our thermal conductivity, times A, the area through which the heat is, the surface area through which the heat is traveling, and the partial derivative of our temperature profile with respect to X. One note about your textbook: be careful not to confuse your variables. So earlier in the book, our book uses Q dot to mean big Q dot, capital Q dot, to mean ventilation, which is a flow rate. And in this chapter, they use a lowercase q dot to be energy transfer. All right, so with this equation, and this is the equation you probably saw, at least in a similar form in previous classes, where our Q dot is the heat transfer rate. BTUs per hour, or watts, so English versus metric units. A is the area normal to the heat flow. So this is important, so the normal word. So it's the area normal to the heat flow. So if you have a surface, it's the heat that's flowing through that surface, not the area of depth. Okay, so hopefully we'll be able to visualize that. When we just talk about conduction by itself, sometimes it can be confusing, but when we start to put things together, it can become more confusing when we're talking about which area are we discussing as we put together conduction, convection, radiation. And we begin to pull out materials and properties of the properties of the materials that we're using and putting them together. So it's always important to ask yourself, which area are we talking about? All right, and then this is your temperature gradient. So it's the first derivative of the temperature profile, which is the temperature gradient. So if this is our surface that we're looking at, and then this is kind of a view looking into the heat transfer through the material. So let's just say we have a couple of planes inside our material, and we have two temperatures, 2 points that are at 2 different temperatures. if our temperature 1 is greater than our temperature 2, then our energy flow will be from the higher temperature to the lower temperature. So our temperature profile can be represented by T2 minus T1 over X2 minus X1. Other forms of the conduction equation might look like so in this case we have these apostrophes, in this case there are two, and they serve to signify whether you're doing things on a per area basis, a total energy basis, or a per unit of area basis. Okay, so let's see. There's a talking while writing thing. Let me just scribble that out. Okay, negative k dt dx times a over L. So up above we had k times area dt dx. This is total energy that's already pulled the area in. If you want to do it on a per area basis, you just leave out the area term, or if you want to do it on a per unit area basis, then you end up with something like this, where you have area divided by length, where length is the length of the surface and not the depth of the heat transfer. Let's get some units on here. So if you're on a per area basis, you need per area in there, and if you're on a per unit area basis, then you end up with a length unit in the denominator. And let's do a little sketch to kind of help us better think about this over total area, per unit area, or per unit per area, per total area, per unit length area. Okay. So if we have a wall section, and it has a surface area A, so this facing surface, and we have some heat transfer going through it. So we have heat moving from one side of the wall to the other side of the wall. The wall has a thickness of X, and the length of the wall section is L. Then you can express this Q as the total amount of energy that passes through the entire surface area, which is our governing equation up above, or we can say there is so much energy per unit of surface area, which is this one, or there's so much energy per unit of length of wall, which is this one. And then some other ways you might see this equation cropping up. It's the integration over the wall surface, or over the area of this equation up above. K A T dx. So we've seen that version already. We also might see delta t, delta x, and we might see it expanded out as minus k a t2 minus t1 over delta x, or that x2 minus x1. Alright, and then one final way we might see this, A delta T over R, where R is the thermal resistance of the material that the heat is passing through. So it's just a conversion between K and R. or UA delta T. So these are the versions that we're seeing in our book, where this UA is overall heat transfer coefficient of the building envelope, and this is the temperature differential on each side of the building envelope, so inside the building versus outside the building. All of these equations are representing the same thing. These are just different ways you might see them show up. All right, the last thing that we're going to talk about with respect to conductivity is the different measures of resistance. So I already mentioned like K and R. And, we have a number of ways to represent thermal resistance. So let's review those, introduce them and review them. In your book, you have table 5.1a and b that has a sampling of material properties that include these thermal properties. Page 124 and 126 in your book. And in class, we took a look and already worked through some examples. We will work through some examples that will use the values from this table. For everything you're going to do in terms of this class, these are the tables that we're going to use. We'll pull everything from there, or else it will be given to you outside. But it's important to recognize that in a real-world setting, this table is not comprehensive. So you'll want to make sure that you're able to access the properties for the material that you intend to use. All right, so values that we have to represent material properties with respect to their resistance to heat transfer. So R is resistivity. Units, meters squared Kelvin per watt, or foot squared hour, degrees Fahrenheit per BTU. K is called conductivity. And if you were listening earlier, I said K is thermal resistance because a lot of times whenever I'm talking about the different ones, I just call them all thermal resistance and then make sure that I'm working within the bounds of the correct units for each one of them. But each one has their own specific name. So R is resistivity, K excuse me, K is conductivity, and C is conductance. Now here's another abbreviation to pay attention to. So be careful to not confuse C for conductance with degrees Celsius. And we use them both inside of the same equations. So it's really important to be careful not to confuse yourself. So degrees Celsius when we're referring to temperature, and C when we're referring to conductance. It's unfortunate, but it's really about, in this case, accounting and making sure that you know what you've used in the right place, and in terms of a problem that you're paying attention to what the problem is saying. You confuse yourself very quickly trying to put one in for the other. All right, so also some of our units in our tables will have Kelvin, and some will have Celsius, and you can see a mix here, and you'll see it pretty widely. But it's okay regardless whether it's in degrees Celsius or Kelvin, and we can use those interchangeably when we're talking about thermal resistance, because when we do our heat transfer calculations, we're looking at a temperature differential. All right, and then you would get a value of each of these for a specific material, but we're going to be putting materials together in order to build our structure. So we're going to be combining materials in order to make wall sections. And at some point, we're going to want to put the values together to get an overall representation of the thermal resistance. And so U represents the overall heat transfer coefficient. So if we go back to the conduction heat transfer equation I showed you, you saw a UA delta T. As we move through our other modes of heat transfer, you'll see why we introduced this U, because when we get into mixed mode heat transfer and we want to combine our modes of heat transfer into an overall heat transfer, we need some means to combine not only the different materials but the different types of heat transfer, and so we start to put them into a common reference value. Another bit of kind of terminology or notation that you might see, this R prime, or R with an apostrophe, is representative of unit thermal resistance. And we might see this when we're talking about a plain wall surface. Or more commonly when we're looking in radial units for things like cylinders. And in HVAC, many of our ducts are cylindrical in shape, so we do run into heat transfer through cylinders. So we need to be aware of the use of unit thermal resistance. And if we want to put that into a heat transfer equation, it looks something like this. Yeah, and just to kind of sketch it so you can put the two of those together. Looks like what we've been looking at so far. There we go. Let's see. So this U value that we were introducing, let's start to put it together in terms of what it looks like combined with our thermal resistance measures. So if we look at our resistivity, U is equivalent to 1 over R. If we look at in unit thermal resistance, then it's 1 over the unit thermal resistance times area. So if you recall, there's an area in the denominator here. And if we kind of manipulate a little bit, get us into that heat transfer equation we saw earlier where Q is UA delta T, UA is the equivalent of 1 over this unit thermal resistance. All right. So those are some of our terms and notations. And then we are going to end by talking about how we can represent thermal resistances. We are going to use the analogous representation of an electrical circuit. So visually it looks the same. Mathematically it has a little bit of a caveat we have to take a look at, but we're going to, let's see, look at resistance to heat flow. Modeled as an electrical circuit. Where this R prime, this unit thermal resistance, can be a combination of our unit thermal resistances or just our resistances. But if we want to do it this way, we can combine a little bit, extend it out a little bit further. So where we have some wall depth with some material that has a resistivity, and another piece of wall that has another resistance. Your areas do have to match, but your wall depths and your materials don't have to match in terms of this combination. In terms of the way I'm writing this equation for the combination. And we can kind of look at this as, here's a wall section with 3 different components. I happen to be drawing them with similar depth, but you don't it doesn't have to be that way. So we have some depth of material 1, some depth of material 2, and some depth of material 3, and some thermal property of each one as well. And then we have a temperature at one surface and a temperature at the last surface. And where we're really going with this is we can represent this as what we call a thermal circuit, which is kind of analogous to representing electrical circuits. Where this is our R1, this is our R2, and this is our R3. All right. If we wanted to look at just a single element from this, so this is our material with thermal conductivity K. Here's our analogous circuit with a resistance, a temperature 1 and a temperature 2, and a heat flow moving that direction. We can look at series elements, which is kind of what we have depicted up here in our first kind of introductory example. Series elements. So these are 2 different materials. And some heat transfer through. If you think of it in terms of our analogous circuits, the heat transfer through this portion must be the same as the heat transfer through this portion. So your Q is sort of like your current flow in your electric analog, where the overall unit thermal resistance is equivalent to the R1 plus the R2. And you can make this an overall circuit where you have an overall thermal resistance that represents the combination of these 2 individual thermal resistances. Now here's where it gets tricky. If you have parallel elements, the math doesn't look exactly the same as the electronic analog. It is weighted by the surface area. Okay. So A1, A2, and you have a Q1 and a Q2. Okay, this is one material, this is the second material, and the electric analog to this, I'm trying to get through. Looks like parallel circuits where you have a resistance through one material and a resistance through the other material, and the overall heat transfer is the sum of the 2. I apologize that my pen is failing and I don't have another one immediately handy, but we're almost done. All right, and your areas just a moment. Oh, much better. Okay, and your areas add up to the total surface area that you're working with. So when we want to combine these parallel elements into an overall R, we do, so let's see, combine. So in electronic circuits, it's 1 over R. But in thermal circuits, it's proportional to the area, okay? So this is a key difference that you'll want to note when you're combining into an overall thermal resistance. So you got to make sure you have that A term in there. So A over, so that the total surface area over the combined R is equal to the area of your path 1 over the resistance of path 1 plus the area of path 2 over the resistance of path 2. Okay. All right, and that's where we're going to end with our discussion of conduction heat transfer. The next section is going to be on convection heat transfer, so tune back soon to continue on with heat transfer and building structure.